So in lesson 3.2, we're going to talk about domain and range. It is very important that we know this concept as you inch yourself toward taking calculus in the future. Domain is the set of x's or the input into a function. When you're looking at the graph, go from left to right. So you always want it to follow that number line order. That's why we've been talking about that interval notation. So that means go from left to right. So what x's were used in the function? What x's am I allowed to input? Now, unfortunately for us, the range, we really can't necessarily answer too much about the range without having a graph to look at. So domain, we might ask for you to tell us algebraically. But for a range, you may have to look at the graph. So it is the set of outputs. What y values am I getting out? And if you look at the graph, you want to go from the bottom of the graph to the top of the graph. That's what that stands for. Bottom of the graph to the top of the graph. What y values? So you always want to think of y values as height and x values a stretch. So how does it stretch from left to right? Range, you want to think about y values. How does it travel up and down? The range are the heights on the graph. The domain are the x's on the graph from left to right. So when we look at this first example, when they are asking us to give the domain and the range, now because this is a set, a discrete set, meaning it's a countable set that I can go, okay, I have these 3 items in there. For the domain, we'd usually just use a capital D. You put the squiggly brackets, and we're just going to list out the x values. So it's just 4, 5, and 8. Now, for domain, when it is a list like that, you don't have to have it necessarily in least to greatest order. I like to do it for my brain because if there's a long list, I'm less likely to have forgotten some particular item on the list. Range, you're going to use a regular R. Now, let me show you the difference. For range, I just use an R. For real numbers, see how I put like a double back on it. So that means range, that means real numbers. So just so you'll know my notation, and most mathematicians, if you take math higher than this, they'll use that same sort of notation, okay? I try to prepare you for if you take math in the future. Now the range, you're just going to list out the y values. See how the b repeats itself? See how we have a b here and a b here? For range, it doesn't ask you how many times you've used it. It's just saying, what values did you use? It's just a list of those things. So when we list those, we're just going to put b and 0. Okay, I can never make the right bracket. Well, I can't make the brackets in general, but not that they look any good, but there you go. Okay, let's look at our second example. So when you're using a graph to depict the domain and the range, you want to travel across the graph from left to right to find your x values or your domain. You want to talk about the graph from the bottom to the top when talking about your range. Okay, and we are going to use interval notation. No, we're not. I'm going to use both. See right here? See where it says write your answer as inequalities? We'll do both, okay? Okay, so if you notice for our x values, so compare our graph with the bottom here, our x values. The lowest x value is 0, the highest x value is 16. So for interval notation, our x values go from 0 to 16. Now, when you're a x value stuck somewhere between 0 and 16, the inequality is you just say x is less than or equal to 0. I'm sorry, x is greater than or equal to 0, but less than or equal to 16. okay? So if they want the inequality, that's what you're going to write there, okay? Now, for the range, we want the lowest value to the highest value, heights. You always think for range of the heights on the graph. The lowest value, look at our y value. The lowest value is a 0, but the highest value is a 400. And because that graph is showing everything is colored in between that, for interval notation, the range goes from 0 to 400. So when we write out the range in inequality form, our lowest value is 0, our highest value is 400. And you would want to talk about those being the y values. So domain are the x values you use from least to greatest. Range is the y values from least to greatest. If this graph had arrows on it, if it was a true linear function instead of just like a linear segment, our domain and range would be all real numbers. See how here you could pick all real numbers if that were the case. Do we have any questions about example 2? Okay. So here it says to graph the function f of x equals negative 1/3 x plus 9, and what is the domain and range? So we know how to graph that. You can even think about that in slope-intercept form. So start here at 9, count down 1/3, down 1/3. I like to stretch it across my graph. It'll give me more of a sense of what my domain and range is going to be. And then make your linear equation. Okay. Now, domain and range, let's talk about that. What x values are you allowed to input into a linear equation? Are there any x values that we have to skip because it messes the linear equation up? Are there any x values you have to skip for a line? Can I plug in 2? Can I plug in 7? Can I plug in a fraction? Can I plug in 0? Just, think about that for a minute. Are there any x values that I have to skip? There are not. So the domain is all real numbers. Now you can take a shortcut. You can make the real number r. You could also say that it goes from negative infinity to positive infinity. In ALEKS, I'm pretty sure that the words all reals are a choice. You would just hit all reals. Okay. Now the range of this graph, what y values are we going to come across? Well, just like the x's stretch forever from left to right, so that's why our domain was all real numbers. The lowest value that this graph will go to, well, it's going to go forever down. So I can pick whatever low heights are going to come out that I want. I can pick however high I'm going to get it. So you always want to think of range as low to high, the heights of the graph. So in this particular one, our range is also all real numbers, or negative infinity to positive infinity. Now remember, these are the set of x's, these are the set of y's. Note the difference. The domain, or what am I allowed to input? There's nothing that messes up a line. You can plug in whatever the heck you want. You can plug in fractions, decimals, percents, square roots, and anything you want. And so remember that. And then this graph will stretch out. Now the only type of linear functions that will not have a domain and range of all real numbers are vertical and horizontal lines. Kind of mess that up. Vertical and horizontal lines might just have 1 point for their x if it's vertical, 1 point for the y if it's horizontal. So that will mess it up. But every other line, if it just has a standard positive or negative slope sort of thing going on, it's all real numbers. Everyone good with that example? Okay. So remember, the domain of all polynomials is always going to be a real number. the domain of a polynomial. What's a polynomial? Well, let me give you some examples. F of x equals x squared plus 2x minus 3. That's a polynomial. F of x equals 2x plus 7. That's a polynomial. F of x equals 2. That's a polynomial. Any polynomial at all will always have a domain of all real numbers. There's nothing that I am prevented from plugging in. I can plug in whatever the heck I want. Remember, domain are what are the inputs. And if I can input, and you can have something, like 7x to the 5th plus 2x to the 4th plus 3x plus 7. Those are all polynomials. And as we go through this chapter, and I think maybe into chapter 4, we are going to discuss more of the qualities that a polynomial has. But think, what am I going to not be able to plug in? Well, I can plug in whatever the heck I want. And so that's the beauty of a polynomial, a linear function, all of those types of functions. You are going to be able to plug in whatever you want for the domain. So if you look at it and see it's a polynomial, you can say, yep, domain's all real numbers. And feel free if you want to put the little all real number symbol. I don't know how Alex does it all the time, but it seems like the all reals was a choice that they give you sometimes. So just so you know. Okay. Remember, I'm going to keep showing you interval notation. It's not going anywhere. It's a subset of the real number line. Let's do this one in interval notation, and then let's look at a graph that's a little more complicated. So this says that we want the x's between -5 and 0. I'm not allowed to equal -5, but I am allowed to equal 0. So remember, at 0, we will have a closed-in dot. At -5, we will have an open dot, and then we will color in everything in between. Now it says write the set using interval notation. So those are the x's that do not include -5, but do include 0. So remember, the equal to gets a bracket, the non-equal to, the almost -5 gets a parenthesis. So I think into my brain, almost. I'm almost at -5, that's a parenthesis, but I'm allowed to stand at 0, that's a bracket. So you'll see we will revisit some topics. Alex will revisit some topics that are important to what goes with the particular lesson. So now let's actually apply this to a graph that has some pieces and parts and weirdness to it, okay? So we've got this graph here. It says the entire graph is shown. Write the domain and range using interval notation. Okay. So the first thing I think of, and occasionally I will draw, I call him my math bug. Okay. And if he can only walk from left to right, so he can only walk to the right, what you want to think about is what x values will my math bug be allowed to stand upon? What x values will he hit along his journey? Okay. Is he allowed to stand at -4? No. So if we follow the x-axis, he's not allowed to stand at -4. He can stand at all of these. Where does he have to stop? At 4, right? And can he stand there without falling through? No. So you think about that when you're thinking about, as he walks along from left to right, then what x values will he hit along the way? So the domain of this function in interval notation, the value he can almost get to, the littlest value he can almost get to is -4. He can get everything in between, and the next value that he can almost get to without stopping is +4, but he can't stand there, okay? So he can almost get to -4, and then he can almost get to 4. And you use parentheses to indicate that those were open circles and he would fall through, okay? Now, that math bug can only go from left to right. My next math bug goes from the bottom of the graph to the top of the graph. Okay, so his job is to go from the bottom to the top. The bottom to the top indicates the range values, the Y values that he's going to hit. So you're always going to compare it with the Y values that he hits along his journey. So if he starts at the lowest value, what's the lowest value he can almost get to? -4. Now he can't stand there. Remember, there's a hole there. So he writes that as a parenthesis and not a bracket. Now he's walking up the graph. He can get to -2, -1.5. He can get to 0. He can get to a height of 2. He can get to a height of 3. Where does he have to stop? 4. Can he stand on 4 without falling through? No. So we're going to include that with a parenthesis. Okay. So remember, domain is the X values that are used from left to right. Range are the Y values from bottom to top. Picture if you were walking along it, if you're a little math bug, where am I going to stand? What am I going to do? Okay. Any questions about example 5? Okay. So now let's talk about the things that do have problems. I told you polynomials, linear functions, those are all great. But there are some things that get messed up. And the first thing we're going to talk about are fractions. Fractional denominators cannot be equal to 0. So if we go to try to input something that makes that happen, it's going to make the fraction blow up. So to find the values that we must exclude, you're going to set the denominator equal to 0. And those are the values that we have to skip in our domain. They're called excluded values. So any place where the fractional denominator would equal 0 are values that we have to skip. They are excluded values. So fractional denominators cannot have 0 denominators. So fractional denominators cannot be 0. That's super important to remember. So it is one of the things that can cause an issue. And that's in what's called a rational function, a fractional function, or we have some type of variable in our denominator. So Alex is going to ask you sometimes, what are the restrictions on this? What are the domain on it? What values do we have to skip? And that's what they're talking about. Where would we get a 0 denominator? Where would we get a 0 denominator? So in example 6, we have this rational expression, and it says find all excluded values for the expression. That is, find all the values of t for which the expression is undefined. If there's more than one value, separate them with commas. So a fractional expression, that type of equation, will be undefined where our denominator equals 0. So this is how you find it, very easy. The excluded values are just where our denominator equals 0. So you're just going to take out the denominator. Who cares what's in the numerator? The numerator can be whatever you want it to be. You're going to take your denominator, you're going to set it equal to 0, and you're going to solve for that variable. So that's just a simple equation. Now, if it has a power on it, you might have to use a quadratic formula or might have to factor it. But if it's just linear like this, that 4t plus 8, we know how to solve those. Subtract 8 from both sides. Divide by 4. So our excluded values are when t equals -2. So for Alex, you would just put in -2. That's your answer. Now, if it is something that is factorable, you know, say it has like a t squared on it, you make it more than one value, just separate them by commas. Just think about how we go about solving things like that, okay? Now, what I'm talking about is one like example 7. See how the bottom there is a quadratic. So when it says to find all excluded values for that, we're still going to do the same exact thing. You're going to write down your denominator equals 0, and you're going to find those values. Now, there are multiple ways to do that. Let me show you 2 different ways to solve this. Now, obviously, you can use the quadratic formula. A is 1, B is 0, and C is -81. You could do that. That's torture if you don't, you don't have to. You could factor it to be t plus 9 and t minus 9. And then you could get where does t plus 9 equal 0? Where does t minus 9 equal 0? So that's a good way. Factorization is nice because you see the parts very clearly. So we get values of -9 and +9. So that's a legit way to go. You can do that. Now, another way to do it is if we look back at this one, since there's only a t squared and no other t's in our problem, we could get t squared alone. What's going to get rid of that square? The square root. What do you have to put in front of it? Plus or minus. Here's why. See that the factorization, the reason I like it is because you see the plus and minus that's just out there, it's showing. Here you can forget. So when you put that square root on there, don't forget, put a plus or minus. You still get plus and minus 9. Either way you do it, whether you use a quadratic formula or factor it, or because it's a perfect square, you just solve for it. I don't care. But Alex is going to need 2 answers. I am going to need 2 answers, 9 and -9. So just be careful with that, okay? Okay. Let's take a look at this one. Now here, see, it's different. The last 2 just said, find the excluded values. You list them, bam, 9, -9, okay? Look what they asked here. You have to be careful how they're asking the question. They say, domain, find all the values that are not in the domain. They're asking the same exact thing. Now, I'm going to tell you what the domain is in a minute, okay? But they did not say to tell you the domain. I think the next one does. Yeah, okay. We're going to do the exact same thing. We're going to set the denominator equal to 0. If it's a factorable quantity, I would assume that's the way to go. If it's not a factorable quantity, please go ahead and use the quadratic formula. That's going to get you your 2 values that are excluded. 18 is 9 and 2, which adds up to 11, so I know it's a factorable quantity. That's x plus 9 and x plus 2. Don't forget, that means I get 2 values. Where does x plus 9 equal 0? Where does x plus 2 equal 0? So you split it apart, 2 values. Quadratic formula gives you 2 values unless it's a perfect square, then you get 1. So it doesn't happen too often. So you should usually get 2 unique values. So we get x equals -9, x equals -2. So what are the values that are not in the domain? Those excluded values, -9 and -2. But if they asked us for the domain, let's think for a minute. Our little math bug is walking along. He gets to -9. He's like, oh, crap, there's nothing there. I got to leap across it. And then he keeps walking. Everything's good until he gets to -2. And then he's like, oh, crap, there's nothing there. I got to leap across it. So let's show you how that domain is going to look. So the math bug can walk from -infinity, and just before -9, he found some kind of hole or asymptote or something funky happened in the graph. So he leaps across it. He can keep going again until -2, and he leaps across it. And he can keep going again for the rest of his little bug life. Okay, so let's discuss this again. Nothing is excluded. Nothing is excluded. Oh, I can't stand on -9. The math bug jumps across it. This means on the other side of -9, almost -9. I can keep walking until I almost get to -2, and then I can leap across it. So you'll notice there's a skip and a skip because that is only a singular excluded value at -9 and a singular excluded value at -2. That's how you write that. Because the math bug, if you were to draw that function in Desmos, the math bug will either get a hole at -9 or -2 or an asymptote, like a complete break in the graph. Okay. So then in example 9, it asks you to find the domain. See the difference? So they say interval notation or union of intervals. That's what this is. That's what that is. See, I put the union symbol to say it can be this piece or it can be this piece or he can jump across and go to that piece, okay? So let's start with the first one here, f of x. For f of x, we need to skip values where x squared plus 2x minus 8 equals 0. Now they're nice. They've made them factorable, at least this one. So we get x plus 4 times x minus 2 will give us that factorization, or that quadratic. So we get excluded values when x plus 4 equals 0 and when x minus 2 equals 0. So it's pretty common to have two excluded values if your denominator is a quadratic. So we get excluded values of -4 and +2. Now you're going to skip them in number line order. Domain is number line order. So our domain is going to go -infinity, skip -4. So that's the skip at -4. Keep going until I hit +2. That's the skip at +2. So I have a skip of -4 and a skip of +2. Everything else would be in the graph. And you can put that into Desmos, and you will see at -4, there is an asymptote. At 2, there's actually a hole in the graph. You don't really see it in Desmos too much, but if you walk your finger like it's the math bug across that point, right at that point, it'll say undefined. It doesn't show that hole there. There's a hole there. Okay, now let's take a look at this one. If we set x squared plus 49 equal to 0, we get that x squared equals -49, or x is plus or minus 7i. Square root of 49 is 7, square root of a negative is I. That is not on the real number line. There are no real excluded values. Those are not on the number line. They can't be excluded. I don't care about them. So for G, the domain is all real numbers. There's nothing that messes that one up because the graph is only depicting real numbers. There's no complex numbers, no imaginary stuff on a graph. So if you get excluded values that are numbers containing i's, whether you solved it this way or using the quadratic formula, if you get negatives under the square roots, those aren't counting for excluded values. There's a lot to take in here, I know. Okay, we're not done, unfortunately. We have to talk about square roots and then we're done. Okay, so polynomials, linear functions, they work perfectly. Fractions, we have to exclude denominator zeros. Square roots, we have to exclude the negatives because remember, the number line is depicting real number. It's called the real number line on purpose. So square roots only work where the inside stuff equals, is greater than or equal to 0, where the inside stuff is greater than or equals, we can leave the equals there, or equals 0, okay? Square roots work where the inside stuff is greater than or equals 0. So to find the domain, the inequality naturally happens. You just set the inside greater than or equal to 0. Now, be careful because Alex might want a interval notation. So if you get an inequality, that's why we've been practicing how to put that into interval notation. If it's a square root in a denominator, then you have the same issue you had before. It can't be equal to 0. You got to exclude the zeros. But you can still use where the square root is greater than 0. So just be careful, okay? The two main things, even in calculus, that we worry about for a domain are fractions and square roots. If you combine them, then you have both problems. But you have to worry about fractions and square roots. Because of the real number line, we only get positives under our square roots. So when they say, find the domain of this function, and you see a square root, get in the habit of taking the inside, setting it greater than or equal to 0. That's not the inside, is it? Take the inside, x minus 6, and set it greater than or equal to 0. That's why we practice solving inequalities, because now you just solve for x, and we have the domain. Now, it might not be in interval notation, but we have the answer, okay? So we would add 6 to both sides. So it's just all x values greater than or equal to 6. On the number line, we know what that means. Colored in, shade to the right. So the interval notation that Alex is searching for, they want you to enter a bracket on the 6, go to infinity. A bracket on the 6, go to infinity. Always go from left to right on the number line. Always go from left to right. Has to be a number line order. That's what interval notation is depicting, a section of the number line. I can go from the 6 to the rest of my life to infinity. Okay. Now let's do another one. Let's look at how 10 and 11 are different. 10, you could rewrite that as the square root of 10 over the square root of x plus 6. So we're only worried about the denominator. That's the only one that has an x in it. So you don't write x plus 6 is greater than or equal to 0, because is a denominator allowed to equal 0? No. So you're just going to put, where does x plus 6, where is it greater than 0? Okay, so if the x is just hanging out like normal, you use greater than or equal to. If the x is in a denominator in your square root, you have to just use greater than, because the equal to messes up a fraction. Okay, so subtract 6 from both sides. X is greater than negative 6. Have an open circle on your 6, because you can't, negative 6, because you can't include it. Shade to the right. So our answer is negative 6 to infinity. So if the x is just in a square root, the equal to 0 is okay. If the x is in your denominator of a fraction, equal to 0 is never okay. So don't include it. So that is the difference between those two problems. Be careful. And if you're going in, Alex, and you get to something and you read the instructions and you're unsure, that's why you take these notes. Open up the notes. What did Mrs. Hott do for a problem with those instructions? Oh, she only set the denominator greater than 0. Oh, that one she included the equals to 0. So watch, use these as your guide, okay? So here is your domain problems. Just for these ones, you're going to use the graphs to answer your domain. These ones, just think about, we said polynomials have all real numbers. Fractions, we exclude the denominator, equals 0. Square roots are greater than 0 unless they're in the denominator. Okay, so that's that. Don't forget that tomorrow at the beginning of class, I am going to hand you this paper. You have to accurately draw those 9 graphs. You have to give me the equation. It looks like the blank version. So if you want to get the blank version out of your 3-1 notes and try to do it again, that's a good way to study for the test at the beginning of class tomorrow. So you're just going to have to draw an accurate picture, give me the equation, fill in the chart, and there were a few little pieces that I told you could get yourself some bonus points. Okay? Yes. I don't know. I was thinking somewhere around like 25 or some points or something like that. Probably about around 20, 25, something like that. Okay, there you go.